This video is about zero-knowledge PCPs and how to construct them for leakage-resilient secret sharing. And it's based on joint work with Carmit, Hazay, and Venkitasubramaniam. And it's a project that I really love. And the reason why I love this project is because it combines together what I believe are two of the most surprising primitives in cryptography and complexity theory. So the first is zero-knowledge proofs that let you prove a claim without revealing anything except the fact that it's valid. And the second primitive are probabilistically checkable proofs that let you verify a proof without even reading it. So today what we're going to do is we're going to put them together to get zero-knowledge PCPs. And these are really useful objects. So for example, they're used to construct succinct arguments. And the highlight of our work is that we're going to get this zero-knowledge guarantee without paying any price for it. And we're going to do this by viewing the information that the verifier gets on the proof as leakage, and then we'll use leakage-resilient tools to protect against this leakage and get zero knowledge. So there are a couple of primitives that we're going to talk about today. And let me start by just explaining what these primitives are. So the first is probabilistically checkable proofs, or PCPs. So these are probabilistic proof systems where there's a randomized verifier that has oracle access to a proof. This is just a bit string. The verifier is going to read only few symbols from the proof and then check whether an input X is in some NP language L. And we're guaranteed that if the input is in the language, then the verifier would accept it given an honestly generated proof, one that was generated by the efficient prover given the NP witness. And we also have a soundness guarantee, meaning that if the input is not in the language, then the verifier would reject it with high probability, regardless of the purported proof that it got. So today we're going to talk specifically about zero-knowledge PCPs. So zero knowledge, I know, is a concept that needs no introduction to this audience, but still let me tell you what it means in the context of PCPs. So we're going to compare the real world execution with an ideal world execution. In the real world, the verifier has oracle access to the proof that was generated from the NP witness. And we compare its view with a simulated view that was generated given just the input X. And we want this view to be simulatable even against a malicious verifier that makes many more queries to the proof. So if the verifier reads the entire proof, of course we can't get any zero-knowledge guarantees. We need to somehow restrict the verifier. And we're going to restrict the number of queries it can make to the proof. So specifically, we want that the view of any verifier that makes at most Q star queries to the proof for some a priori bound Q star. This view is simulatable given just the input X. And this, of course, requires a randomized prover. So the bottom line is that zero-knowledge PCPs hide the witness, similar to how zero-knowledge interactive proofs hide the witness. And there are several parameters that we care about in the context of zero-knowledge PCPs. So the first is the query gap. What is this? It's the ratio between Q star, which is the number of queries a malicious verifier can make without violating zero-knowledge, and Q, which is the number of queries the honest verifier has to make to get soundness. And in general, we want this ratio to be as large as possible. The second parameter is the quality of zero knowledge, whether the simulator is efficient and runs in polynomial time or inefficient and runs in exponential time. And the third property is the adaptivity of the honest verifier. How many rounds of interaction, how many rounds of queries does it need to make to the proof to get soundness? And in general, we want a non-adaptive honest verifier that makes a single round of queries to the proof. So these are the parameters that we care about. And what do we know about getting these parameters? So the notion of zero-knowledge PCPs was first introduced by Kilian Petrank and Tardos in 1997. What they do is they take standard PCPs and they combine them with an information theoretic commitment primitive called a locking scheme to get zero knowledge. And their construction is quite attractive. So first of all, they get an exponential query gap, which is great. It means that the honest verifier only needs to make a polylogarithmic number of queries to the proof to get soundness. They also have an efficient zero-knowledge simulator. But unfortunately, they have an adaptive honest verifier, and this is inherent to their construction. So this means that to get soundness, the honest verifier has to make several rounds of queries to the proof. And the adaptivity is inherent because of two reasons. So the first is this use of the locking schemes. So these are commitments that have both information theoretic hiding and information theoretic binding. And to get these two properties together, the decommitment phase has to be interactive. So it means the verifier is adaptive. So this is one source of adaptivity. The other source is the transformation itself, the way in which they combine these standard PCPs with the locking schemes. So later on in 2016, Shai et al. Set out to solve this problem and to get a non-adaptive honest verifier for zero-knowledge PCPs. And they do so by proposing a new paradigm for constructing zero-knowledge PCPs, in which they view the queries of the honest and malicious verifiers as leakage on the NP witness. And then they use tools from from the leakage resilience literature to protect against this leakage. And they get the same type of exponential query gap with a non-adaptive honest verifier, but unfortunately, their zero-knowledge simulator is inefficient. And they actually show that this is most likely inherent to using the leakage resilience tools that they use and the way in which they use them. So what we do is we construct the best of both worlds zero-knowledge PCPs for NP, meaning we have a non-adaptive honest verifier and efficient zero-knowledge simulation at the same time. The query gap in our constructions is square root, meaning the honest verifier reads a square root Q star bits from the proof. And this should be compared to a better query gap of exponential query gap in previous works. We also go beyond zero-knowledge PCPs and show the first zero-knowledge PCPs of proximity with a non-adaptive honest verifier. Prior to our work, we didn't know how to get this, even if we were okay with an inefficient simulator. And along the way, we give a better analysis of a zero-knowledge PCP, which is implicit in a work of Ishai, Kushilevitz, Ostrovsky, and Hazay from 2007. So they construct a zero-knowledge PCP with no query gap, meaning to verify the proof and get soundness, the honest verifier has to make as many queries as the malicious verifier. And we improve the analysis to get a square root query gap. So these are our results, and let me sketch the way to get them. So I'm going to start by briefly explaining the improved soundness analysis for the ZK-PCP of ICOS 07. Then I'll explain our paradigm, which is an alphabet reduction that preserves zero knowledge. And this uses leakage resilience, and I'll describe the specific leakage resilient primitive that we need to use. And finally, I will tell you how to go beyond PCPs and get zero knowledge PCPs of proximity with a non-adaptive honest verifier. So let's begin with the ICOS 07 zero knowledge PCP. So ICOS 07 were actually interested in constructing interactive zero knowledge proofs, but they implicitly construct a zero knowledge PCP variant over a large alphabet. So usually we're thinking of PCPs and zero knowledge PCPs as being just a bit string. And here it's not a bit string, it's a string of symbols over a large alphabet. So this construction is quite attractive because it has efficient simulation with a non-adaptive honest verifier, which is a good starting point because this is what we want to get. The main drawback of this construction is that there is no query gap. So to get soundness, the honest verifier has to make as many queries as the malicious verifier. And what we do is we give an improved soundness analysis showing that you can get a negligible soundness error with fewer queries, specifically with a square root number of queries. So now with our improved analysis, the ICOS zero knowledge PCP has efficient simulation with a non-adaptive honest verifier and a query gap. So it seems to be what we want, but it's over a large alphabet. And this is problematic, as we'll see in a minute. So we need to reduce the alphabet size and somehow get a proof that is just a bit string. And this is what we're going to do next. So we're looking for an alphabet reduction for zero knowledge PCPs. And if we look at standard PCPs, there are several techniques to reduce the alphabet size, and they're quite complicated. But when you look at them, you realize that the reason that they're complicated is because in the context of PCPs, people are really trying to optimize the parameters. the number of bits that the verifier reads from the proof and the proof length. In the context of zero-knowledge PCPs and cryptographic applications, we're anyway going to get a blow-up proportional to the security parameter. So these optimizations are not as important. This means that the natural starting point would be just the naive alphabet reduction, where you take each symbol and replace it with a bit string. And this preserves soundness. If before the verifier read these three symbols, now the verifier would just read the entire strings, bit strings that represent these symbols and emulate the original verifier. So this slightly increases the query complexity from 3 queries to 9 queries, but now these are queries to bits. The main issue here is that this naive alphabet reduction doesn't preserve zero knowledge. So before, the malicious verifier had to read full symbols. Now a malicious verifier has a larger budget, right? Instead of 3 queries, it can make 9 queries. It's not restricted to querying full bits. And actually, a malicious verifier won't read full symbols. It will read, you know, some subset of symbols, some subset of bits from many symbols, and potentially a malicious verifier might be able to read a bit from each and every symbol of the proof, which means we cannot use the zero knowledge of the underlying zero knowledge PCP. So the issue is that the malicious verifier can read parts of symbols. And our solution is to view this reading of parts of symbols as leakage, and then using tools from the leakage resilience literature to protect against this leakage. But wait a minute, this idea of viewing the information as leakage and so on was already used by Hazay in 2016. And they prove that if you use leakage resilient tools, you're going to inherently get an inefficient simulator. So what's the idea here? So the thing to notice is that Hazay et al. Were using leakage resilience to protect computation. So they were using a quite strong primitive, which are leakage resilient circuits. And they do show that by using these circuits, you can't get efficient simulation unless NP is contained in BPP. We're doing something completely different. We're using the leakage. We're interpreting something that is entirely different as the leakage. And we're going to use leakage resilience to protect something different, which is the information instead of the computation. So the leakage resilience that we're using, leakage resilient encodings, this is a much weaker primitive, and this allows us to circumvent the negative result of Hazay et al. So what are these objects that we're using, these leakage resilient encodings? So you can think of them as error correcting codes, but in error correcting codes, we're usually thinking of the encoder as being a deterministic algorithm, whereas here, the encoder is going to be a randomized algorithm. And again, we have a deterministic decoder that recovers the secret from the code word. And the leakage resilience guarantee is that a small subset of code word bits reveals nothing about the secret, in the sense that you start out with 2 secrets, M and M prime, and you randomly encode them into 2 code words, E and E prime. Then leakage on these 2 code words is statistically close. So these few code word bits that you leaked reveal no information about the secret. So equipped with these leakage resilient encodings, let's take another go at designing an alphabet reduction. So the first step, as before, would be to take the large symbol and replace it with a bit string. But now we're going to encode each of these bit strings using the leakage resilient encoding and replace it with a code word C. And now let's see how this helps with a zero knowledge simulation. So when we need to simulate the answers to the queries of the malicious verifier, there are 2 types of symbols. There are symbols that are queried a lot, and we call these symbols heavy. And notice that there can't be too many of these because the malicious verifier is still restricted to making not too many queries to the proof. So because there are only few of these large symbols, we can use the zero knowledge of the underlying system to emulate them, to simulate these symbols. And then we can just honestly generate an encoding of these symbols and answer any leakage queries to them. For the other symbols, they can't be queried too often because again, the verifier is restricted in how many queries it can make. And because they can't be queried too often, we can use the leakage resilience of the leakage-resilient encoding to answer these queries, because we know that few leakage bits on the encoding reveals no information about the underlying secret. So we do get zero knowledge. However, notice that to perform this simulation, we need to know in advance which symbols are heavy and which are not, because we're simulating them differently. And this means that what we're getting is zero knowledge against a non-adaptive malicious verifier. And I want to pause here to kind of explain the difference in the adaptivity of the honest and malicious verifier. So having a non-adaptive honest verifier, which is what we set out to get, this is a feature of the system. It means that you can get soundness by just performing one round of queries to the proof. So that's great. But getting zero knowledge against a non-adaptive malicious verifier, this is a restriction of the system, because it means that if the verifier can make 2 rounds of queries to the proof, all bets are off. We have no zero knowledge guarantee. So what we want is soundness with a non-adaptive honest verifier, but zero knowledge against an adaptive malicious verifier. And I want to explain a bit more thoroughly why we have an issue here. So we start out with a proof, and we can think of the proof as being divided into sections. Each section is the encoding of a different symbol. Now the verifier starts reading bits from the proof. And it reads these bits, and at some point, some symbol becomes heavy. Once it becomes heavy, meaning the verifier queried many bits from this code, from this encoding, we can ask the underlying zero-knowledge PCP simulator for the corresponding symbol. Now we need to continue leaking on this. We need to generate an entire encoding of this symbol, which we didn't know before. And this encoding has to be consistent with the leakage that we've already provided on this section of the proof. This means that we need a way to explain in retrospect the leakage as a leakage on the encoding of this symbol. So leakage resilience is not enough. We need some equivocation property. And this goes on and on. The verifier might go on leaking, and other symbols might become heavy. And again, we'd need to equivocate the encoding. So the primitive that we need is not leakage resilient encoding, it's equivocal leakage resilient encoding, also known as reconstructible probabilistic encodings. So these encodings have a randomized encoder and a leakage resilience guarantee, as in standard leakage resilient encodings, but they also have an equivocation property, which means that you can explain the leakage in retrospect as the encoding of any arbitrary secret. So here's the scenario. Starting out with some secret, it's encoded randomly into a code word. And then this code word is leaked on. And then at some later point, after we've already obtained the leakage, we're given this arbitrary secret M prime. It's a different, might be a different secret. And now we need to somehow explain this leakage as an encoding of M prime. So an equivocal leakage resilient encoding has a re-encoder that takes the leakage and this arbitrary secret and generates an entire encoding of this secret, M prime, which is consistent with the leakage. And we want this encoding to be statistically close to an encoding that was randomly generated for this M prime, randomly subject to being consistent with the leakage. So this is the equivocation property of equivocal leakage resilient encodings. And in the paper, we also generalize this to the realm of secret sharing and introduce the notion of equivocal secret sharing. So now equipped with this, with these leakage, equivocal leakage resilient encodings, let's go back and finish the alphabet reduction. So we're going to take the large symbols, replace them with bit strings, and encode the bit strings. But now we're going to use an equivocal leakage resilient encoding. And this lets the simulation go through. And why is that? It's because when we start out, we think of all the symbols as being light, and we simulate queries using the leakage resilience of the encoding. Whenever some symbol becomes heavy, we ask to get that symbol of the proof from the underlying simulator of the underlying ZK-PCP system. Given this symbol, we can equivocate the encoding of that symbol in a way that's consistent with the leakage. And this is because of the leakage-resilient encoding is equivocal. So to sum up, we get zero-knowledge PCPs for NP that have both a non-adaptive honest verifier and a zero-knowledge and have zero-knowledge with efficient simulation. We get this by designing an alphabet reduction for PCPs that preserves zero-knowledge, and this alphabet reduction uses equivocal leakage-resilient encodings. Applying our alphabet reduction to the ITC 7 zero-knowledge PCP gives us these zero-knowledge PCPs for NP, which do indeed enjoy the best of both worlds, because before we didn't know how to get a non-adaptive honest verifier with efficient zero-knowledge simulation. So in the few minutes I have left, I want to tell you how we go beyond zero-knowledge PCPs. So these PCPs that we've been discussing, as I said, are very useful for some applications. But for other applications, they're not as good because they require the verifier to read the entire input X, which means the verifier's running time is at least linear in the input length, which might be prohibitive in some applications. And also, there's no privacy guarantee for the input in this case. And the question is, can we do better in applications where we either need privacy of the input or we want the verifier to be sublinear? And the answer is yes. So we can use PCPs of proximity or PCPPs. So these are similar to PCPs, but instead of having the input locally, the verifier has oracle access to the input, similar to the way it accesses the proof. And we're guaranteed that the verifier accepts input in the language and rejects inputs that are far from the language in relative Hamming distance. And the notion of zero-knowledge PCPPs is similar to the notion of zero-knowledge PCPs. The only difference is that now the verifier doesn't have the input. It only has oracle access to it, and so does the simulator. So now the view of any verifier making Q-star queries to the input and the proof is simulatable with just Q-star queries to the input. So this means that zero-knowledge PCPPs hide the entire witness, the way that's the same as zero-knowledge PCPs, but they also hide most of the input X. And this is the main advantage over zero-knowledge PCPs. And the parameters that we care about are the same as for zero-knowledge PCPs. We want a large query gap with efficient zero-knowledge simulation and a non-adaptive honest verifier. So this notion of zero-knowledge PCPPs was first introduced by Shai et al. In 2014. They use the same paradigm as Kilian, Petrank, and Tardosh. They extend it to the PCPP setting, and they get zero-knowledge PCPPs with exponential query gap and efficient simulation, but unfortunately with an adaptive honest verifier. And again, this is inherent to the transformation. So the only way we know of getting a non-adaptive honest verifier is using the techniques of Ishai et al. From 2016. But unfortunately, because they use leakage-resilient circuits that protect computation, we can show that their technique inherently does not extend to PCPs of proximity. So before our work, we didn't know how to get zero-knowledge PCPPs with a non-adaptive honest verifier. And what we do is we show the first zero-knowledge PCPPs with a non-adaptive honest verifier, and we get the best of both worlds because we also have efficient zero-knowledge simulation. And the same query gap as in our zero-knowledge PCPs, meaning square root. And the high-level idea of the construction is to first construct a zero-knowledge PCPP variant of the ITC 7 zero-knowledge PCP, and then extend our alphabet reduction to PCPs of proximity. So let me sum up. So we construct zero-knowledge PCPs and PCPPs that enjoy the best of both worlds. The technique is to construct an alphabet reduction that preserves zero knowledge. Along the way, we also give a better analysis of a zero-knowledge PCP of ITC 7. And the main open problem that remains from our work is to reduce this query, to improve this query gap. So we want it to be as large as possible. Hopefully, we can get something which is exponential as in previous works. And I really hope that we'd be able to improve this and get all of the properties that we want at the same time. So thanks for tuning in. See you all in the Q&A.